Very good day to all industry leaders, my beloved lecturers, my fellow classmates, and everyone else in attendance for this FYP Day exhibition conducted by the Department of Aerospace Engineering, University Putra Malaysia. So my name is Chong obviously, final year undergraduate from Aerospace Engineering, UPM, and today I'm going to conduct a presentation on my final project topic, which is parametric study and design optimization of supercritical carbon dioxide cycles for waste heat recovery from jet engine. And my supervisor in charge is Dr. Xiaoming. So according to a very popular thermodynamic reference book, from Cheng et al., I think most of us has come across it. There are like three essential ways to increase turbine efficiency on a more broader perspective. Increase engine efficiency, which are increasing turbine inlet temperature, any modifications to the basic cycle, and increasing the efficiency of turbo machinery components. So, as aforementioned our topic, we are integrating a basic recovery cycle into the jet engine. So the second objective or green region fits the bill. And waste heat recovery. Waste heat actually a form of unused heat released to the surrounding by any form of heat engine, be it car engine, jet engine, or even power station. So what we're going to do is to recover this unused heat and convert this heat into useful work to feed it back into its main branch or main system, so that the main system becomes more efficient. And there are like three main categories of waste heat, but we are going to only focus on high grade, which is temperature range of more than 400 degrees Celsius, which is because jet engine function is to direct combustion process. And this is like we can see that some of the thermodynamic cycles that is applicable for this process. But in the end, we selected SCO2 cycle as our cycle of choice, mainly because you can see the waste heat source temperature of 350 or 850 degrees Celsius is the common waste heat temperature produced from a jet engine. And other than that, there are like a few more benefits in selecting SCO2 as our working fluid. First of all is the desirable physical properties. You can see critical condition can be achieved at 31 degrees Celsius, which is very easy to achieve, and 7138 megapascal, which is slightly hard to achieve but still achievable. And once you have reached the critical region, it will be much more denser and much more viscous than its gas counterparts. But the main thing here is that it can achieve high values of specific heat at constant pressure, or high CP. And as we know that high CP means that that particular material, which in this case is supercritical carbon dioxide, can hold large amount of heat with a small volume of SCO2, which will contribute to the second point, which is compact thermal machinery size. That means with a small volume of SCO2, it can hold the same amount of heat when compared to a steam Rankine cycle, which is a much larger volume. That's why, as you can see here, it is like 10 times smaller than steam Rankine cycle. That means the compressor of a SCO2 cycle will be 10 times smaller than a steam Rankine cycle. However, it needs to maintain a minimum cycle pressure of 75 kilopascal, which is much higher than a steam Rankine cycle, which only needs a few kilopascal. But as according to the Boyle's law, high temperature, high pressure. So it will result in a high turbine outlet temperature and also a large amount of waste heat to be harvested. But it has a limit for the minimum cycle pressure. We can only achieve it until around 300 kilopascal due to empirical constraints. So with a max pressure ratio of 4. And these are like some variations of the SCO2 cycle. First one is the single flow cycle, much simpler. And the second is split flow cycle, which is a bit more complicated but more components, and it also split the flow at different points of the cycle. And hence we reach our problem statement. Of course, the main thing is to produce fuel efficient engines via this solution, and to lower operating costs of industry leaders on their fuel. And how we're going to do that, first thing is to do a quantitative analysis on different SCO2 cycles. We're going to select a few of them from the previous list to see which one is the best one, and to integrate that one into the actual operating condition of a jet engine. So these are the objectives of my research, but the main point of note here is to look at the second tab, is to achieve as low thrust specific fuel consumption or TSFC value as possible, so that it will be low TSFC value will equate to better fuel efficiency. So, average literature review, there are some papers that I research on, but the main thing I look at is the application here. Like I have go through a lot of papers, but in the end, I have not found a single one that say that apply this cycle into a jet engine. So that's why me and my supervisor, Dr. Shamimi, is trying to see if the benefits of this cycle into other applications can be equally beneficial to a jet engine. Another point of note, the best performing configuration mostly is recompression and recuperation, which is validated at the next slide here. So you can see here, recompression and modified recompression is the best performing in the middle there. But nonetheless, other cycles other than preheating and turbine switch for number 3, most cycles hover above like 35% of cycle efficiency or around that, which is very respectable for a thermodynamic cycle. So after all research I've done, in the end I decided to select 3 cycles. First one is a simple radiant cycle. Although it's not a proper recuperation cycle, but there are two main um, there are like two main functions to it. First thing is to act as a control of the whole research, so the other cycle has some like weird data coming out. We can always go back to this cycle to see what went wrong. And the other important reason is we replace the working fluid of this simple cycle into SCO2 so that to see that it's increase or decrease in performance compared to other working fluid with the same cycle. And you can see here the semi diagram here is plotted at S1 plus, and this TS diagram is plotted at Microsoft Excel, which I'll explain later. And the second cycle that I selected, one variation from the Singapore cycle is the recuperation cycle, which is also a simple cycle, just that you are adding a recuperator to a basic Brayton cycle. And the third and final one is the recompression cycle. I try to select another variation from the split flow cycle, which in this case is the best performing one. It looks a bit more complicated, but basically it's just adding extra component of compressor and also recuperator, and also mixing and splitting for external parts of the cycle. And after selecting our S0 cycle, I wanted to select a gas turbine jet engine that can be used as our case study. So in the end, I decided to select the CFM International LEAP due to its popularity. As you can see here, installed engine variable of around 22,000 is almost 2 times more than its nearest competitor. And these are like some of the benefits of engine for future studies. And this is like the specifications of the engine in particular. And there are like 3 variants, but we're going to look at the LEAP 1A variant due to its popularity. And the 2 main variants we are looking at is the TSFC and also the max continuous thrust. So this TSFC is being measured during its max continuous thrust period. So what we are going to do is try to achieve a TSFC lower than 14.4 once we integrate this basic recovery system into the jet engine. So these are like the 2 softwares that I have used. I mentioned earlier those 2 diagrams being plotted from these 2 softwares. So the first software and the main software in use is the S1 Plus software. It's a chemical process simulator. It's not too widely used in our industry, but it's very common in the chemical engineering field because it allows us to model and simulate complex calculation and a process and build a process model by it. And which indicates we are using a thermodynamic cycle when investigating it. So why not that we try this software to produce the results that we wanted. And after we have seen the results, these results will be formulated in Microsoft Excel so that we can present the results graphically. And these are the work organization flowchart, a basic flowchart that apply to all other of my classmates when doing the FYP. But the main thing here is to ensure our model validation achieve a mean absolute percentage error of or MAPE of less than 10%. Which is the main thing here. And the second one is software simulation flowchart, which is the flowchart that I have followed throughout the research. And these are the fundamental assumptions, just basic thermodynamics, so that to alleviate my research calculations. And these are the main part of the software input. This is the input parameters and assumptions. But the 2 main things here we look at is the compressor. You can see inner temperature, inner pressure is 32 degrees Celsius, 7.5 megapascal, which is slightly above the critical condition of the SCO2. It is because we wanted to ensure the carbon dioxide is at critical condition throughout the cycle process. And the second thing is the heater. you can see the waste heat temperature is at 550 degrees Celsius, which is my smack in the middle of the ranges of SCO2 cycle, as I mentioned at the beginning, which is 350 or 750. So 550 is right in the middle. And this is the other parameters are inputted. So due to constraints of the software and other, like too many parameters influence this parameter, like temperature, pressure, etc. I decided to take this from a reliable reference source, hence this value for the flow rate of CO2 of working fluid, and also the flow speed ratio. Also, I took it that only applies to recompression, because in speed flow ratio, not all, it doesn't split in 50-50 when it's speed flows for recompression. And in this case here, 0.705, that means 70.5% of the flow stays in the main flow, and other almost 30% will go to the speed flow. And the EOS used Ping Robinson. S1 Plus is a numerical software, simulation software. And these three are the main performance parameters that I will gauge on. The first two, output power and thermal efficiency, will be in use to select the best cycle, and the TSFC I mentioned before, we see the performance in engine. And also sensitivity analysis, maximum cycle pressure and basic temperature are the two main parameters that I have outer. So maximum cycle pressure, I set the maximum to say 30 megapascal, because as I mentioned before, technology constraint, the maximum pressure ratio at CO2 might set at 4. So critical condition is 7.5, so times 4, maximum that can reach is only 30. And for basic temperature, 300, 400 or 700 is still within 350 or 750 degrees Celsius set by the previous slide also. And hence we reach a result in discussion. So I have obtained a reference source. In fact, it's a paper from my supervisor, Dr. Chong, and I inputted, like mimicked the same input conditions and values, and after that I try to compare the differences, and I've achieved error of 5.3 and 6.1, which is well within our stated value of less than 10%. After we've done the evaluation, we continue on our research. And these are base case results. These are all the values obtained via S1 Plus. And the two main things here, as I mentioned before, my parameter network and thermal efficiency. So in terms of network, recompression performs way better than basic Brayton. But in terms of recompression, you can see the power values skew out a bit too high. But I believe it's mainly due to scaling factor. As proven by a compressor and heat input and recuperator, a compressor work main and recompression cycle, main and recompression compressor have similar work produced as per my research. So this one looks okay. And the other one, heat input and recuperator, high temperature should have higher heat input than low temperature ones. So you can see here, it solidifies the fact it is a scaling factor. So in terms of thermal efficiency, we can use this value, the value of recompression on it. So as you can see at the second row, the green color, recompression has the highest thermal efficiency compared to recuperation and basic Brayton. So as I mentioned just now, sensitivity analysis, the first parameter that I vary is the waste heat temperature. So you can see here, recompression as indicated by the green line has the highest thermal efficiency when I vary the basic temperature, followed by recuperation, and followed by Brayton, which is quite low. But nonetheless, this proved the fact that by increasing the basic temperature, the thermal efficiency of all cycles will increase, except for Brayton, which kind of plateau, but in fact is decreasing slightly from 18.79 to 18.1 throughout the basic temperature range. And this is the network done. So recuperation, the network done with recuperation is slightly higher than Brayton, but as we mentioned at the previous slide, recuperation has a higher thermal efficiency than Brayton. And this is the recompression cycle for a network, because the reason I put it as a separate graph is because the value is much higher, but due to scaling factor, this value is irrelevant. And other than that, I also use the heat recovery efficiency to compare between these two cycles. The reason for me using this is because it's just to gauge like how much of heat is left at can be retained by a particular cycle. But although Brayton has a higher heat recovery efficiency, we know that this amount of high amount of heat cannot be retained by the Brayton cycle because it will be released by the condenser. Hence, you can see, as compared to recuperation, hence you can see it although has a high recovery efficiency for the Brayton, but in terms of network thermal efficiency, I mentioned in the previous slides, recuperation is better performing, in which the same can be said of maximum cycle pressure, but this time the graph has a different trend when we vary the waste heat temperature, which is the decreasing trend when we try to increase the maximum cycle pressure for all cycles. But when compression between cycles, the result is still the same. The compression is still the best performing compared to recuperation and Brayton. And this network done also decreasing, same as thermal efficiency, and this is the recompression cycle for network done. And after we have selected the best cycle, like we cannot use the recompression cycle values anymore, so we only look at Brayton and recuperation. But as you can see here, recuperation and Brayton cycle has improved the TSFC by 40 to 39%. 40 to 39%, actually, this is a very huge number, and which is very very good. And in terms of the graph, although it's not that obvious here, TSFC for recuperation is slightly lower when achieved by recuperation, 1.2127 from a thrust of 0 to 8.48 to the power 10 to the power negative 3 at this endpoint, when compared to, which is slightly higher than Brayton. And the engine thrust is determined by the maximum thrust with 143.05 kilonewton for the LEAP 1A radiant. That's why, hence this range of values. So in conclusion, we selected recuperation as the most suitable cycle, and also the performance, as you can see, is very beneficial if we integrate the waste heat recovery system into a jet engine, in which our hypotheses are justified. And these are like some of the benefits, pros and cons of each cycle. And although recompression is highest thermal efficiency, we can see that a lot of computation occur in this research, and there are a lot of components to be used. And if you look at waste heat Brayton, although it has the lowest thermal efficiency in network, high heat recovery efficiency means that in low and medium grade waste heat recovery, although it doesn't, in low and medium waste heat recovery, it doesn't need to retain much heat, so it is suitable for that. In terms of recuperation, it's one of the simplest recuperating configuration and one of the highest performing. Therefore, we selected this as our optimum SCO2 cycle. And these are the recommendations that I can say for my research. First one is optimization and mass flow rate of working fluid. I think we need like more sophisticated software to determine this, so that we can result in a better value on network efficiency for our cycle. And the second thing is the further research on recompression SCO2 cycle. It has proven by my thesis it has the highest thermal efficiency, but due to compilations the network cannot be produced. So I think we can do further research on this to exploit its advantage and benefits. So that is all for my presentation, and thank you.